Okay. All right. Let's do it. What do you got for me?
Yeah.
Hypothesis one. Okay.
So basically, like this is the tricky part right here, and
Mm-hmm.
it's not tricky on this one because it's this. The sequel is really easy. Like
Mm-hmm.
you only care about one table, um, and then any manipulation in pandas. Um, so what I did that I think is probably useful
Mm-hmm.
is I didn't just do the tests. I
Mm.
added some print statements.
Okay.
So to be like the null hypothesis can be rejected, it can't be rejected, just
Right.
so I don't have to look at the p-value
Yeah.
alpha,
Yeah.
and allowed for them to be passed in variables. Like this is the t-test here, but and I've set it to default to regular t-test, but you can pass in to be Welsh's t-test by just saying equal var to false.
Okay.
Um, I think that functions usually help. Like this is actually a thing that you like got me doing because I know you've done like a bunch of functions that helped you out with
Yeah.
doing like more streamlined.
Yeah.
So
So
I
you're
did
kind of
was
like wrapping the functions in
yeah, I'm
like
just adding some
your own
stuff to.
custom, right? And you got the print statement. You know what might be interesting is how you have the print statements that say that the null hypothesis can or cannot be rejected.
Yeah,
I wonder if there's a way to do it where like you could store the null hypothesis as a string in a variable, and then like to make it even better, like when you run the function, it says the null hypothesis that blah 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 is rejected. You know what I'm saying? I don't know. That's a thought.
yeah. I mean, I could at least, worse if that doesn't work, you can like the normal test has its own assumptions, like
Hmm.
that they're from the normal distribution.
Right.
Just add
Yeah.
that in the
Add that part
text
in.
there.
Right. 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 Right.
Yeah, that's probably a good idea.
Yeah. So we have that. Okay, cool. So you got the normal, you got the go up a little bit. So
Normal, Manwitney,
variance,
t-test, and variance are the ones I've
variance.
used so
Okay.
far.
So get to. Did you do? Show me the stuff about Tukey that you were talking. I'm interested in that.
Yeah, so Tukey is it's like not the easiest or most like intuitive thing
Mm,
to run
yeah.
at first because you're like I'm comparing two things.
Yeah.
Um, and the problem is that's not how the arguments are set up.
Mm,
So here is the syntax that Ben suggested,
mm,
which is to run multi-comparison and then Tukey HSD on that. So
mm,
first thing I ran, so first argument is basically a variable,
mm,
and then the second is grouping it. So like the different groups
mm-hmm,
that, so here we're trying to figure out the impact of discount on quantity.
mm-hmm.
So for each group of discount, it does them in pairs, and then it checks the quantity and sees if there's a difference in the mean of the
Right.
quantity.
Okay.
So this is just the important thing is I got tripped up on this for hours is how to pass
Mm-hmm.
this in because I
Mm,
was expecting to be able to pass in like
mm,
originally I had two data frames,
yeah.
one without discounts at all and
Yeah.
one with any discount.
Yeah. So
So I had to attach.
exactly what is multi-comparison? What does that do?
So multi-comparison is a function that basically, I mean, I was just reading the docs. I should like um, multi-comparison.
Let's see. I'm gonna pull it up too. What is it in stats?
It's in statsmodels.stats.multicomp.
Okay.
I strongly recommend reading the documentation for it,
Yeah.
including the source, because the source actually let me know that there's like a visualization that helps with the Tukey once I
Yeah.
understand better how to interpret this visualization.
When you say source, what do you mean?
The docs should have, let me find an example of a stats model docs.
Like the ones that you pull from like within the notebook, like the help function, or the ones that you find online on their website?
They should be the same,
Yeah.
but
Because I'm
what
looking at
that's
this right now. class statsmodel.sandbox.stats.multicomp.multicomparison.
Yeah, that looks about right. Oh, am I in the right? Yeah, I just think I closed a bunch of tabs. So multi-comparison. So like navigating this, the stats model docs aren't the best.
Yeah,
I'll say that.
yeah, I hear you.
The Pandas docs went from being really good to not having enough examples, which is weird. Like a bunch of pages that are important lack examples now. Sucks. It's just like slow internet today. So here you can click on the source.
Okay. I see what you're saying. Okay.
For multi-comparison,
Yeah.
which I think I can get to.
Oh, so that's the source takes us to the actual function that they've coded out, and then you can read the comments, I guess, or something?
Yeah, you read the doc string, basically.
Right. Okay. That's good to know.
It is just a wrapper around the method of multi-comparison, so you don't need to run this specific code. You can run multi-comparison. Multi-comparison. Yeah, so it's tests for multiple comparisons. Like up here, whoa. There's some good notes on this. Just to get some, like, it's like, oh, this thing needs to be updated. You know, it's always useful to read that. But Tukey. This is sort of like the different parts of Tukey here. So here is a thing that I found really interesting to read. The results object, or the results class, which takes an object of the results from the test. And like this was the moment where I'm like, I should read the docs more, because
it contains
a plot method. It contains a plot method that's super useful. Though I'm like not sure how to read the plot exactly.
So I guess source is where it's at. I didn't even know.
Yeah, the docs themselves were helpful, but then
not even helped. There's like barely anything in the docs. Like they don't even explain.
They're a start. And then like this group's unique right here gives you what these groups correspond to, like the different groups that are down here. An easier example is I ran the one about gender, and here you have group 1, group 2, and then it shows the groups at the bottom. Yeah, the important thing is to use one sort of pandas series each for the indage, like the variable that you're measuring, and for the groups, like its labels, the different ways it can be different groups.
And then it seems like it's doing like a group by kind of, and getting the unique groups from the series that you pass in, and
it's
then
comparing each possible pair, basically.
Each possible pair of the unique groups found within the series that you pass in. So you pass in a series, it looks at what the unique groups are in there, and then it does permutations of each possible pair of those groups in that series. Okay.
Yeah, and then this is really helpful right here, is reject. It's whether or not you can
It'll just straight up. Okay. So if the p-value is, where do you specify the threshold for the p-value?
You can specify alpha to whatever. So like alpha.
By default, I'm guessing it's probably 0.05.
Yep.
Okay.
Which is what I've been using. So
yeah, that's pretty standard. Okay, that's pretty useful, yeah.
And hopefully it tells like which direction the mean difference is in.
Yeah. Right. See, I had started kind of doing that manually. What I did was I had started just like, my next step was going to be to like, all right, well, I had pulled out all the means for each group, of discount. So like, well, what's the mean quantity for each discount level? And then my next step was I was wondering, what do I do with that now? I didn't realize Tukey's is the way to go. Tukey's kind of does that for you,
Yeah, multiple comparisons of
right?
means.
It
Yeah,
just does. It just does that. It just straight up
once
does.
I got it working
Yeah,
after hours, like of not knowing
yeah.
what I was doing.
That's awesome, man. You saved me hours trying to figure it out. Thanks.
Yeah, look at some of my comments of being confused on
Yeah.
Slack and Ben helping me out to get to the conclusion there.
Mm,
And I did a little write up of my understanding of it.
yeah.
Like, is just like, and Ben was like, "Yeah, you pretty much got it." And then he
Okay.
dropped in some good links. It's one of the more
Yeah.
recent.
Yeah. I'm gonna go back and
ones
look at
on
that. Where does James talk about Tukey?
there. I think he talked about briefly in the last study group, but
Mhm.
not. I don't think he ran it, for
Yeah.
example. That's probably something to ask him to go over.
Because I don't feel like Tukey's is something that we covered in the actual lessons, right?
I don't think so.
Yeah.
We covered Cohen's D.
Right.
We didn't cover some of the like. I don't think did we cover
Non-parametrics.
Levine
I don't think so. No.
variance?
I think maybe we may have done Levine for the variance, but I
Yeah.
know that we definitely didn't do. It does not talk about the non-parametric tests in the lesson. So like Mann-Whitney-U was not anywhere in the lessons, and I first heard about it on one of James's study groups.
Oh, yeah, that's one thing that I'm still not sure about is whether, like, is the workflow of when to use the Welch's t-test versus the Mann-Whitney-U when you
Yeah.
have two. I have to look at that again.
That was my next question is like, so what test is the Tukey's using when it's doing that pairwise comparison to test the means against the null hypothesis? Do we know?
It's using something called the Tukey's range test, which is got its own sort of mathematical implications that I
Is
have.
it parametric or non-parametric? Do we know?
Oh, that's a good question. It's worth looking up.
Like, what are the assumptions? Do we have to be mindful about when it's applicable?
Yeah, there was Ben posted a little bit about some like pitfalls you can run into it, but assumptions. Sort of tests. Actually, I usually like when I'm making notes to myself, I put them in Markdown like this.
Put them in Markdown. You know what? I had this idea of like somehow being able to tag the comments, and then you run the source code of the notebook to like literally scrape it to pull the questions so you could have them in one place. I don't know. I had an idea.
There's probably a way of formatting to do that.
Yeah, or probably a widget that's already been built or a plugin that kind of does it. But
that like highlights all comments or something, I'm sure.
Something, or like gives you a way in which to sort of sort out your comments in a way so that if you have questions versus to-dos versus whatever, and then you could just go on the back end and then pull out all the questions. So then in the study group, you have the questions or.
Yeah, it's worth looking into what widgets there are because I think like the more organized my notebook is, the faster I get things done, the better I get things done.
Yep, I hear you. Yeah.
Yeah. But yeah, those are the big sort of things about Tukey's is like knowing what to pass in, which is like your value versus your groups.
Right.
And then kind of how to read this, which is the comparison of the group, the mean, your p-value, and whether or not you reject. And then there's a plot, which these are standard errors.
Yeah.
I've seen similar plots like this, but like in this context, I'm not sure how to read it. I have to look into it.
I think that would be
plot simultaneous.
Probably like the range of quartiles or something. It's between.
Yeah, it's the range of standard error, I think, for each mean.
Yeah. Well, here's another thing so if you go up a little bit to the table for Tukey's, now the whole objective of this exercise or like using Tukey's is to this is to tackle the second part of the question, which is we want to study at what level of discount do we notice more effects, right? It's to see, well, how much of like an effect does the discount have? And if the discount goes up, does I guess the effect size go up or something?
Yeah.
But here, what's happening? So to answer that question, though, what I'm wondering is it really useful to be comparing values between discount sizes? Should we
Well,
not
it's
only look at?
comparing against zero is the
Is
thing.
it always comparing against zero? That's what I'm saying.
No, several of these rows are redundant. Is
Yep.
my understanding. Like everything underneath here, basically.
Yeah, that's exactly what I was going to say. Is like because it's when comparing 0.1 to 0.2 or 0.5 to 0.10, I don't think we need that because it's not really particularly relevant for the question that we're answering.
You're only interested in those if you're like, what's the different at what threshold, kind of.
Right. Like we're studying the difference between no discount versus different levels of discount and how they affect the quantity bought compared
Yeah.
to having no discount whatsoever. We're not really interested, at least the way the question is framed, is looking at, do you get more? What's the comparison between 10%, 5%? Or maybe we are. I'm not sure, but it's something that's
It's worth
thinking about.
noting if
Yeah.
any of them are like significantly different, which I don't think so.
Yeah.
They're,
Yeah.
they're
So that's my next question. Like, which ones? So let's take a step back. So the null hypothesis that's being tested here is that the mean of quantity bought for the discount level is the null hypothesis is there's no difference between the quantity bought at this discount level versus the quantity bought without any discount applied. And the alternative hypothesis is that no, well, when you have this discount level, the mean quantity bought does tend to be higher.
Yeah.
So in the cases where it has been true, let's take a closer look at those. So we're saying that at 5%, we're noticing that the mean quantity bought is in fact higher, and we can't attribute the increased quantity bought to random chance. The discount is having an effect. And then where else are we seeing it? So we see it at 5%, 15%, 20, 25. What's the highest discount level?
I should have the value counts here.
25.
0.6 actually. Or no, sorry, yeah.
25. Yeah.
0.25.
And the other thing I noticed was that if you look up, a lot of these are like one-offs. You see like how the 3%, 2%, 1% discount level, they're
Yeah.
kind of one-offs. And my instinct was to kind of just get rid of them because they're not.
I think that's a decent instinct to have.
Because it's not really relevant. It's only like 3 times that was applied, so we can't really draw any meaningful conclusions about whether a 3% discount had any effect on the quantity bought because we only have 3 samples.
It's kind of analogous to having outliers, except
exactly.
instead of values, it's samples.
That's exactly right. Yeah, it's like an outlying sample size,
Mm-hmm.
and it's just creating noise, and it's not giving us any insights, and it's just unnecessarily sort of noising up our insights. So I think that might be. So we and you look at like the way that the discounts are structured, it makes kind of rational sense because they're all like in increments of 5%. And the ones that are like outliers are like weird one-off numbers.
Really high, for example, like, or really low.
Really low, yeah. They're generally less than 10%, like, and they're like 1%, 2%. They're like not divisible by 5. But the ones that are divisible by 5s, those are the ones that are like sort of routinely applied. Those are like standard discount levels that seem to be applied.
Which makes sense. Whoever put together this data set was smart in thinking of like partitioning them out like that.
Yeah, but even from a business perspective, I mean, it kind of makes sense of like, you offer discounts in more rounded out sort of incremental 5%, 10%. That makes sense as opposed to like, who cares about a 3% discount? That's like kind of weird,
Yeah, if we cared specifically about like the 3% discount, there's techniques that we can use, like undersampling and oversampling, like to mess with the samples. But that's later down the line.
Yeah.
That's cool stuff though. That is cool stuff.
Yeah.
Yeah.
Cool.
Like fraud is a big machine learning topic, and the problem with fraud data sets is only a small tiny portion of samples are fraudulent. So how do you run the numbers correctly? You have to either like decrease the amount of non-fraudulent or increase the amount of fraudulent synthetically.
Yeah.
So there's a lot of really
I wonder
interesting
if
work
that's a
done around that.
question. I wonder if that's where an area where the concept of power becomes relevant.
I don't really understand power with that.
Yeah.
Like I'm still trying to wrap my head around it. I think working with it will help me.
Yeah.
Um, like I understand effect size a little more now that I've kind of looked at different numbers.
Mm.
Um, but power is like effect size and then more complicated stuff added to it.
Yeah.
So there's that.
I,
But
I I think I kind of have a shaky grasp on power, and like I kind of boil it down in my head to thinking of it like this. Like imagine you have a metal detector at the beach
mm,
and you can up the power on it and you're more likely to get beer caps and stuff, but you'll miss out on less gold coins, right? But then you also collect a bunch of crap. But if you lower the power, you won't get as many beer caps, but you also will miss out on more gold coins. Um,
yeah, it's a garbage in, garbage out kind
kind
of
of like right. Well, it's just like
thing.
it's like a question of like am I willing? Because the whole idea of power is that like well, if you increase the power, you get more false positives, but you
Mhm.
miss out on less. Like you reject the null hypothesis less often, so you're more likely to collect actual instances of correct observations, I guess. But you'll also collect false positives more often. And I don't know if that's kind of relevant to what you're talking about, like in terms of
Yeah,
the fraud thing, where you up it, well, you'll catch more. You're more likely to label more behavior as fraudulent, even though it really isn't. But then you will miss out on less behavior that's actually fraudulent. I don't know if
yeah.
that's might be getting
Yeah,
ahead of
like
myself
in
there.
unsupervised context where you don't know what's fraudulent,
Yeah,
that sounds like it would be super important on the basic statistic level.
yeah,
I've been doing some unsupervised stuff recently with like
hmm,
clustering.
right,
It's really interesting.
right.
I don't know how much we go into unsupervised learning.
Mm,
Um, I think we do, at least like it's in the machine learning section,
mm,
surely.
yeah.
Um, but yeah, let me see if there's any other like big gotchas or anything I did that this was me trying a ad hoc version of Tukey's by like running at different discount amounts, which is not really how you should do that, is my impression. Um,
Say that again. What were you doing there?
so I was running Welsh's t-test and I was running Mann-Whitney U, which I'm still not sure which is the appropriate test to use for this one. I think it's Welsh's.
I don't. I think it isn't Welch's because I dismissed Welch's because it's the variances are off. No, wait, hang on.
Look at the workflow.
Yeah, and then the workflow says that if well, you need to do the Welch's t. No, I'm sorry. For the Welch's t-test, you don't need to have equal variances, but you still need the assumption of normality, if I remember.
Yeah, but the thing is, um,
If it's greater than a group size or something, it doesn't matter.
yeah, our group in
Uh,
this case, the group size is big enough because like
okay.
way bigger than
Well, yeah, that's the other thing.
15,
Like the
20.
workflow was slightly confusing, I think, in the way that it was worded because it says if you have normal data, move to assumption two, equal variance. And if you, okay, so then it's okay. If you fail the assumption on equal variance, use Welch's T. If you pass, use that. But then if we go back here, if you don't have normal data, check if your group size is big enough to safely ignore. If your n is big enough, then move to two. Um, so then that means that even if the n is big enough, we still need to look at the variance.
Yeah, and if you
Um,
fail the variance, then you go to Welsh's t-test.
well, do you go to Welch's or do you go to a non-parametric?
Um, if you
Move to
it
step
looks like
three.
Welsh's is for when you have normality
Right,
or big enough size, but
mm,
not variance.
right. That's my understanding. Yeah,
Non-parametric is for when you have neither.
that's what I thought. Yeah, and it seems that that's the case though in the quantity ordered because we don't see have normality or equal variance among the different um, discount levels. Or am I mistaken in that?
We don't have either, but we have a big enough group size.
So which allows us to dismiss the need for the assumption of normality, or
Uh,
also the assumption of
yeah,
equal
move on.
variance,
Yeah, move on to assumption number 2. Yeah.
which is the variance. So, but
And
then
then
if
if you
we,
fail Welch's t-test.
I don't know if it's just I'm the one who's caught in a loop here, but I'm still kind of
I,
wondering.
yeah, I'm also unsure, which is why I have both in the
Yeah,
notebook so that I can just
yeah,
delete whichever one is wrong.
yeah, yeah. It couldn't hurt. Might as well run both and see what happens.
They're both like one line of code, so
Yeah, might as well. Might as well. You're right.
it's worth asking, you
Yeah,
know,
yeah,
it's worth
yeah.
bringing up. Yeah.